I thought I'd go ahead and make some review recordings for your second semester exam. The first thing that we covered all the way back in January for the first part of this review was exponential functions. Remember, we did lots and lots of growth and decay word problems. I started off the unit with word problems. We said exponential functions always come in the form y equals a times b to the xth power, where a is the initial amount that you have, the initial amount of money, the initial number of bacteria, the initial value of that car. A is the initial amount. And then remember, it branches off. It can be a growth word problem or a decay word problem. And depending on whether it's growth or decay, you determine the value of b differently. If it's an exponential growth word problem, b is equal to 1 plus the rate of growth. If it's an exponential decay word problem, b is equal to 1 minus the rate of growth. So, an example problem should bring this back to you. A new car is worth $30,000 and its value depreciates by 19.2% per year. Depreciates means decay. So, its initial value is $30,000, so that's A. And then since this is decay, B is equal to 1 minus the rate of decay. So that's 1 minus, well, the decimal version of 19.2% is 0.192. So if I grab a calculator, 1 minus 0.192 is 0.808. So my function is y equals 30,000 times 0.808 to the xth power. Now, find the value after 5 years. Well, that just means plug in 5 for x. So that's going to be 30,000 times 0.808 to the 5th power. Okay. Grabbing my calculator, 30,000 times 0.808 to the 5th power tells me that the car is worth $10,331.85 after 5 years. So it's in 5 years it's lost about $20,000 of its value. Okay, now apparently I forgot to finish writing this one. How many years until the value is $5,000? Well, remember, when we first learned to solve this type of question, we used Desmos to find a point of intersection. But as this unit on exponential functions and logarithms evolved, we learned how to use logarithms to solve equations. So this means plug in 5,000 for y. So if I plug in 5,000 for y, I have 5,000 equals 30,000 times 0.808 to the xth power. Well, do I remember how to solve this equation for x? Well, if you were to look back in your notes, the first thing that you would do is isolate the base being raised to the power. And so what would that mean in this problem is that you would begin by dividing both sides by 30,000. So those two cancel. Now I'm grabbing my calculator. 5,000 divided by 30,000 is 0.166666666. So if you round about 5 or 6 decimal places, it's 0.16666 is now equal to 0.808 to the xth power. So hopefully you remember that. Now, once you have the base and the power isolated, we taught you how to change this to a logarithmic equation. Well, 0.1666666 equals 0.808 to the x changes to logarithm with a base of 0.808 of 0.16666 will give the value of x. So I grab my calculator and I just ask it to do the logarithm for me. And remember, on your TI Inspire, you just find the log button, which is over there to the left above the 10 to the x button. So I pull up my log and I put 0.808 in the first box, and I put the 0.166666 in the second box and enter, and it tells me that x is approximately equal to 8.4 years. So if you need more than just that question, ask me to do more in class. Here's another example of the same thing. There were originally 50 rabbits in a population, and the population is increasing at a rate of 15.2% per month. So this time, A equals 50 because that's the initial number of rabbits, and B is equal to 1 plus the rate. So if I move that decimal twice to the left, I get 1 plus 0.152, so that's 1.152. Okay, so y equals 50 times 1.152 to the x power is my exponential function. Population after 10 years just means plug in 10 for x. So 50 times 1.152 to the 10th power. And we're going to grab a calculator and figure out what that is. So 50 times 1.152 to the 10th power on my calculator is 205.8. So there's going to be approximately, I'm sorry, that's 206-ish right there. 205.8 rounds to 206-ish, okay? All right, and then the last question says, but when will the population reach 10,000 rabbits? So is that just like the one we just did? You set 10,000 equal for y. So we have 10,000 equals 50 times 1.152 to the x power. So you divide both sides by 50, and let's see, 10,000 divided by 50, I should know this, is 200. So now what we have is 200 equals 1.152 to the x power. So then doesn't that change to log base 1.152 of 200 equals x? So grabbing a calculator will give us our answer. And let's see, log with a base of 1.152 of 200, x equals 37.4 years. That the population of rabbits is going to grow from 50 to 10,000. So hopefully that's a good review of reading a word problem, building the exponential function, and using logarithms to solve those equations. We will be reviewing logarithms a little bit more in this video. Another thing that we taught you when we were in this unit on exponential functions and logarithms was we taught you how to solve exponential equations. And if you look back in your notes and such, you'll see that I taught you how to solve two types of exponential equations. Ones that you can solve without using logarithms, and equations where you must use a logarithm to solve. So you'll recall I taught you what's known as the property of equality of like bases. The property of equality of like bases says if b to the x power is equal to b to the y power, well, duh, x must equal y. So that's like saying 3 to the x power equals 3 to the 5th power. Well, if that's the case, then x must equal 5. You've solved that equation and you didn't need logarithms. So let's take a look at a couple of examples here. Solve this equation for x without logarithms. Well, you'll notice that the left side of the equation has a base of 6 and the right side of the equation has a base of 36. Well, you got to have the bases the same before you can use the property of equality. So here's what I'm going to do. I'm going to leave the left side of this equation alone as a base of 6. But isn't it true that 36 can be written with a base of 6 as 6 squared? And so then 6 squared is 36, so that's still being raised to the x plus 4 power. So you'll notice now that both sides have a base of 6. So now I can say 3x must equal 2 times x plus 4. Once I have the same base on both sides, I can just disregard the bases and set the exponents equal to each other. So that would be 3x equals 2x plus 8. And if I subtract 2x from both sides, it looks like I get x equals 8 would be the solution to this equation. All right, come over to the second example, a little bit more difficult. The left side has a base of 4 and the right side's a mess, 1 over 32. But are you noticing that 4 is a base 2 number and 32 is also a base 2 number? So watch what I can do. I can change the left side to 2 squared to the x minus 5. The right side I can change to 1 over 2 to the 5th. 32 is 2 to the 5th. Well, now I can keep the left side as 2 squared to the x minus 5 equals, I can change the right side to 2 to the negative 5th power. So now both the left side and the right side have a common base. So now I can say 2 times x minus 5 equals negative 5. So now I can say 2x minus 10 equals negative 5. Add 10 to both sides, 2x equals 5, x equals 2.5 would be the solution to that equation. So hopefully when you're looking back in your materials, you'll see that we learned to solve those types of equations, quiz, test, everything. Now, we also learned some things about logarithms in general, like I taught you how to convert exponential expressions to its equivalent logarithmic form and vice versa. So we say that any base raised to a power equals the answer converts to log base b of a equals p. So, for instance, if I give you the expression 2 to the 5th equals 32 and ask you to convert it to a logarithmic expression, wouldn't the answer be log base 2 of 32 is equal to 5? This expression and this expression are equivalent, like English and Spanish have equivalences. Convert log base 9 of 1 over 81 equals negative 2 to its exponential expression. 9 to the negative 2 equals 1 over 81. So remember, we learned how to convert from one type of expression to the other, so, make sure you're good to go there. Then we learned how to solve some exponential equations with logarithms. And if you go back to the beginning of this video when we were doing the word problems, we already solved some exponential equations with logarithms. But here it is formally. In order to solve an exponential equation using logarithms, step 1, isolate the base to the power. Step 2, change to a logarithm. Step 3, finish using algebra to solve for x. So let's see if you remember this. Example number 1 on the left, 3 times 4 to the x power minus 18 equals 27. Step 1, isolate the base and the power. So what that's saying here is that I'm trying to isolate the 4 to the x. So what I'm going to do is I'm going to add 18 to both sides. And so now I have 3 times 4 to the x power equals 45. Well, you'll notice I still don't have the 4 to the x isolated, so I'm going to divide both sides by 3. So now I have 4 to the x power equals 15. So you see now I have the base and the power isolated. So step 2 says change that to its logarithmic form. Well, wouldn't that be log base 4 of 15 equals x? So what that means is all I've got to do is grab my calculator and type in log base 4 of 15. And, oops, the answer is, pardon me, my calculator's messing up, or I should say I'm messing up. Log base 4 of 15 is 1.95-ish. And that's how you solve that. Okay, looking over at the right side, just another example. Isolate the base of 2 and its power of x minus 1. So what I'd be doing here is subtracting 8 from both sides. So now I have 6 times 2 to the x minus 1 equals 92. Well, I still haven't isolated the 2 to the x minus 1, so I need to divide both sides by 6. So now I have 2 to the x minus 1, and I need to know what 92 divided by 6 is. And it's 15.3 repeating. So if you put 15.33333 about 4 or 5 decimal places, you should be okay. So now change that to log base 2 of 15.33333 equals x minus 1. So now if I grab my calculator and find out what that log base 2 of 15.33333 tells me that that's 3.9386. Well, remember, that's not equal to x. That's equal to x minus 1 this time. So I got to add 1 to both sides as a finishing touch. And of course, I want to add the whole number 1 to the whole number 3. And it looks like x equals 4.9386 would be our solution. So make sure that you can solve exponential equations with logarithms. Finishing up, we also learned how to solve logarithmic equations, equations that already have a logarithm in them. Step 1, isolate the logarithm. Step 2, change to its equivalent exponential form. Step 3, solve. Okay, so one example will do, and I think we'll call this first video done. Solve this equation 3 times log base 5 of x plus 7 minus 9 equals 10. Okay, so this time isolate the logarithm tells me that I've got to do something with that minus 9 and the times 3. So I think I'll add 9 to both sides. So now I have 3 times log base 5 of x plus 7 equals 19. I need to divide both sides by 3. So those 3's cancel out, and I have log base 5 of x plus 7 equals 19/3, which is like 6.3 repeating. So I've isolated the logarithm. So I've completed step 1. Step 2, change that to its exponential form. Well, the exponential form is 5 to the 6.33333 power equals x plus 7. So I'm going to grab my calculator and raise 5 to the 6.33333 power is 26,718.4 is equal to x plus 7. So obviously to finish solving for x, I want to subtract 7 from both sides. and x equals 26,711.4 would be the solution to this equation. On the review handout, you would see that problems similar to these problems reviewed in the video are at the beginning of the review, so you could complete that portion of the review handout accordingly.